Anyway, it's noon, and the Big Ben says that we are supposed to be starting at this time. Let me welcome everyone to the third edition of an event that we started in spring last year. It's called Spreading the Computer Science Gospel. And the goal of this event is to present some nuggets of computer science research that have a broad appeal, that sort of indicate something that everybody should already know if their heart is in the right place, namely that computer science is the new damsel amongst the sciences that sort of connects them all, and that it has everything, sort of a lot to say with its tools, techniques, and way of thinking. There's a lot to contribute to just about any question in science and about humanity, actually, under the sky today. The format for the event is that we're going to have 3 10-minute talk, TED style. The talks will be accessible to a very broad audience. They are not going to require any specific background from the audience. We'll take the 3 talks by María, Grischa, and Henning in this order, and then we will take questions from the audience to the 3 speakers. We're going to start at 12:05 with the first talk. Today's talks will be dealing with 3 different topics. Maria's talk will present how approaches from data science can be used to understand the impact, in this case, of the pandemic on human life. We'll then have a talk by Grischa on sort of collaboration, if you wish, in the age of the pandemic, and how sort of working remotely or physically can influence collaborative work in software engineering. At least that's what the title I could glean from the title. And last but not least, Henning is going to tell us sort of what mathematics can learn from computer science. So our first speaker is María Óskarsdóttir. She's an assistant professor in at the School of Computer Science at Reykjavík University, and she's a data science lady, our data science expert. She has already given a public talk on data science techniques applied to the pandemic a while back, and I know that several of the people in the audience have already attended that talk. María, can you share your screen so that you're ready to start at 12:05? Because we are in Iceland and we do everything sort of at the appropriate time. Thank you. So, María, I suggest that you start.
Thank you, Luca. And thank you for the introduction and for the opportunity to present what we've been working on here today. So the title of my talk is Changes in Mobility Patterns in Europe During the COVID-19 Pandemic, and it's the result of a research summer job that we had going on this summer. So the motivation behind this particular project is that there is a lot of data all around us that can tell us a lot about how the pandemic is impacting us as a community and our well-being as individuals. And we want to do what we can in this regard and try to understand this impact, because as we all know and we all have all experienced, it has affected most parts of our lives. We are working more from home, which means that our daily routine has changed. We don't have to get up as early in the morning. We don't have to sit in traffic to get to work. So maybe we are a bit more relaxed because of that. but also it's of course, caused stress in our daily lives. And of course we cannot, do the social things that we were used to doing before. Our daily routines have changed. We are not traveling in the same way we did before. For example, here in Iceland, we can't really go abroad on holiday. We were kind of stuck here on our island. And then finally, just our daily mobility patterns have changed a lot because we have been staying much more at home. And then on the other hand, well, the reason for all of this is because the governments have taken different actions in different countries. And these actions, they are different, very different from country to country. Some have imposed lockdowns, others insist on social distancing. Some countries have a lot of testing and tracing and putting people in quarantine. So these strategies, they differ from country to country, but also the timeliness of these restrictions has differed a lot from country to country. For example, Spain and the UK, they reported their first confirmed case of COVID-19 on the same day, but Spain waited 6 weeks to impose restrictions, whereas UK waited 7 weeks. And then in contrast, we have Denmark and Norway that only waited about 2 weeks before they had their first confirmed case until they imposed some kind of restrictions in their countries. So the main takeaway from this talk is that I kind of want to show you how aggregated data can tell us a lot about our society and our well-being under the impact of COVID-19. So we can use a lot of aggregated data to tell a great story about how the pandemic has affected us. Researchers are using data and data science in different ways to predict and investigate the impact of the pandemic. In the beginning, this research was focused a lot on trying to predict the spread of the virus from its origin in China by augmenting epidemic and mobility models to get more accurate predictions. For example, to estimate the basic reproduction number and the effectiveness of government action. And these studies that I'm talking about here, they focus on like the human mobility aspect of this. But of course, there are also a whole strand of research that is looking more into the virus itself. For example, what Decode has been doing here in Iceland in analyzing these strains of the virus and trying to see where it's coming from and so on, and how it affects people in different ages and different genders and so on. So this was what people were focusing on a lot in maybe April and May, but now it's kind of shifted. Now that the virus is all around us, it's kind of shifted to trying to understand what impact this pandemic has on us, on our daily lives, on our well-being, and then subsequently as well, the consequences for the economy and the long-term effects of it. So in this particular project that was carried out by a student during the summer, Harpa Steingrímsdóttir, she was on a research summer job here at RU, and she took sources of open data, publicly available data from different directions, and she combined all of them into a dashboard that shows mobility trends in Europe. So on the one hand, she used data from Apple Mobility Trends, which simply shows the number of routing requests using Apple Maps. And Apple made this data public so that people could investigate how, or simply see how mobility has changed throughout, well, since January until now. They keep it quite up to date. And then we accompanied this Apple mobility data with flight data, so number of flights Open Sky Network provides a data set specifically during this pandemic time about the number of flights worldwide. So it's simply a list of all flights in the world during this period. And then we took information from the health organization about the number of confirmed cases and death due to the virus. And we put all of this into a dashboard focusing on countries in Europe. I'm not going to show you the dashboard itself. I'm simply going to show you some of the mobility trends that we saw in the data once we had combined the walking mobility and driving mobility and the flying mobility. So here you can see the walking mobility on the left and the driving mobility on the right for 10 European countries, as well as New Zealand. New Zealand is the black line. Iceland is the dark green line in this plot. And what we can see here very clearly is, for example, for Italy, that was exposed to the virus way earlier than all the other countries, the mobility drops much sooner than for the rest of the countries. So Italy is the yellow line. And then Spain, who was hit next by the pandemic, it's the gray line. And there we can see the drop right after the drop in the Italian mobility. And what we also see is that the mobility is slowly increasing again and reaching this average level, which is the zero line in these plots. But we also see that mobility is increasing again at a different rate in different countries. So if we look at Iceland, which is a dark green line, we can see that our walking mobility has not yet reached the baseline, whereas our driving mobility has. And then what I also find very interesting is that this goes until end of July, this data, and you can see that the mobility is kind of dropping again, which is probably caused by this, the threat of the second wave that was starting to happen at the beginning of August. If we look at the flying mobility, so the data from this Open Sky Network data that we put into our dashboard, so these would be the same countries as we saw in the previous slide. Again, you can see that Italy drops earlier than the other countries, but then you can see also all the countries following very quickly after Italy. And the flights are increasing again, but in contrast to the other figures I showed you, flight mobility has not yet reached the baseline again, because as we know, flights are much less common now than they were at the beginning of the year. But at the same time, if we go back to the driving mobility, that's went very quickly over this baseline. And what we can see very clearly here is that people, they are driving way more than they did before. And this is interesting because, of course, this period, June, July, August, this is the summer holiday period in Europe. And what we can see is that people are clearly driving on their holiday instead of flying like they are more used to. And then when we think about what are the long-term effects of the pandemic, of the impact that we are all feeling, I've shown you already these changes in the mobility trends. People, they are driving more and flying less. In some countries, people that were walking a lot, they are not yet back to their walking baseline. So we can see a very clear change in routine. We can see also, like I mentioned, that people, they are flying and driving instead of flying like they did before. We can also see the variation in the level of harshness in the policy taken in different countries in Europe. Like I mentioned, Norway and Denmark, they reacted quite quickly, whereas Spain and UK took a longer time to react. And then if we think about this in the long term, what will be the effects of this pandemic on us years from now? It's of course difficult to say, but we can see that immediately with data reported by Withings, which is a producer of activity tracking devices such as watches. they have made public these numbers about weight gain of people in different countries. And they have seen that, for example, in Italy, an average person has gained 200 grams during the lockdown, simply because they couldn't, move around like they normally did, go to the gym or whatever they are used to doing. And then the final important thing that we have to think about, I think, is that we can use open source data to investigate our society, like we did in this particular study, and therefore open source data is very important. And that is the takeaway message and the final point of my talk here today is this balance between the collecting and sharing of data. Big companies, they are collecting a lot of data about us, and actually all the apps that we have on our phones are collecting data about us. Maybe not all, but most of them. And big companies, I'm thinking about, for example, Facebook and Apple and Google, that know so much about us because they collect everything. I mean, this event was advertised on Facebook, so Facebook will know who looked at the invitation and who said that they would join this event today. So they know a lot about us, and much more than what we realize. And of course, they are collecting all this data in order to improve their services to their customers, but also for their own gain, because of course they want to make a profit. But then the question remains is, what are they giving back? Like, they are collecting all of this data, but what do we as a society actually gain from all of this data collection? And what will remain when Facebook no longer exists? What will remain of all this information that they collected and that they possessed? And this is very important for historical significance. So if you think about archaeologists that, 1,000 years from now want to investigate our time in history, what will remain for them to investigate? And therefore, I think it is very important for this documentation for these big companies to give something back, like Apple Trends did with this mobility data, so that we can also gain from all this data collection that is going on. And so, and as we saw in this presentation, this type of aggregated data, these number of flights and the aggregated mobility data from Apple can tell a very great story when presented well. Thank you for your time.
Thank you very much, Maria. Let me clap on behalf of everyone. As I said, we'll take questions for every speaker at the end. So let's move on to Grischa's presentation. Grischa is going to tell us on the effect of collocation and remoteness in problem solving in software engineering. Grischa, the floor is yours virtually.
Excellent. I hope you can all see me. Welcome to my talk. My name is Grischa. I'm an assistant professor here at Reykjavík University as well. And if you bear with me for the next 10 minutes, I'll tell you something that you in a way already know, because I'll talk about remote distance calls, distance communication, and related to the pandemic, I guess, at least since the spring, exactly what that means. Now in software engineering, which is my research, so how do we build software systems in a better way? In software engineering, this is a rather common setup because we have teams all over the globe. It's not uncommon to have a team here in Iceland that does development, does project management maybe, but the actual development is outsourced, for example, to companies in other parts of the world, in India and Ukraine, somewhere in Europe, in the US. So we very commonly have these kind of setups where we need to talk to each other over an online connection, sharing slides, sharing video. And sadly, it's not only about small talk, but it's really about solving problems. So what we wanted to know, what we wanted to investigate is how is the effect of having people, well, in the same room or globally. And you know this from your own calls, you know that somehow it feels like remote is just not the same thing. It's not only harder with the technology is also just somehow not as effective. Now, I said my area is software design, software engineering. We wanted to look particularly into a process that is called software design or software architecture, which is concerned with how do you structure the overall software system. So you have to build something, you have to break it down into pieces and decide essentially how to distribute the work. This is very similar to, for example, if you would build a house. That's my usual example. You start with the architecture, you think about how many stories do I need, what kind of rooms do I need, where are they, but also how stable do they need to be, for example, if you have earthquakes or things like that. That's sort of the high level, but then you also often have very detailed design, which is maybe more like the interior design in a house. So where is the sofa, where is the kitchen, where does the bed go, how do we do this in a good way? So similarly, in software design, we would like to know how do we structure the software and then go into details. And this is a really creative process and is really a problem-solving process. You cannot build the ideal system. You have to take certain trade-offs. So we essentially decided, let's look at how teams do this in a co-located way, in a distributed setting, and how do they communicate? How do they talk? The way we analyzed this is we observed, we videotaped a number of designers, pairs of designers that work together, and we looked at something that is in the industrial design community known as design thinking, where you say that if you solve a problem, you are essentially in the problem space, and then you design a solution to it. And you don't do problem space and then you solve it, but you iterate between that. So you might at some point realize, well, wait a second, if we build our house, what happens if there is a lot of sun or a lot of shade? Do we have to change something? So you go back to the problem space and you try to think about, okay, what are our assumptions? What do we know? And if we have clarified something, we go back and solve it. So this is an iterative process. And this categorization is what we use to analyze communication. So our setup, I have to say this is an initial study, so it's not a lot of data yet, but we studied 3 pairs of designers, so 6 designers in total that were in the same room, drawing on the whiteboard, discussing in the same location, and then the same setting in a distributed way, where we had designers in Germany and in Sweden that would talk over an internet connection. They had a virtual whiteboard, so they could draw on an actual physical device, but they would see what they were doing. And they had a Skype connection with video, so they could see each other somehow. And then, as I said, we videotaped this. We looked at when are they in the problem space, when are they in the solution space, and how do they move between them, essentially. Now, the first finding we had here is something that is very obvious. That's exactly what you would expect. In the virtual case, there was much, much less communication going on. And that's simply because, well, it's connection problems, things might be slow, you suddenly don't hear someone because, I don't know, some noise went on in the background, or you start talking at the same time, so everyone has to stop talking and wait and repeat. So it's just less. And that's, as I said, that's maybe not very surprising. That's what we know already, but at least it's a confirmation. The next thing, and that's really interesting then, in my opinion, is that we found that the distributed teams do much, much less of this problem exploration. So going back to our original picture here, they were constantly in the solution space. They were basically just discussing how do we do our software, how do we do it, without going back and questioning what do we actually know about it, what kind of things might be difficult, what have we forgotten. And this is somewhat an indication of why remote meetings feel so ineffective, that we are actually doing all this problem thinking, this problem exploration. We do that individually, we do it in our heads because the communication is not so effective. And then we just come with solutions. How about this? We do it like that. And looking at this, the communication between people, we actually saw that it was essentially 2 monologues going on, just proposing things. And well, they were all circling around here. So that's essentially the point that, well, there was much, much less of this problem exploration going on. Now, this has a number of implications, and we are at an initial level. We would like to study this more, but this is at least an interesting finding that explains why do we actually find remote collaboration so difficult. And for software design in particular, it basically leads to two different kinds of conclusions. You could say that, well, we try to counteract challenges that we have due to the technology. For example, like I do in this talk, that you can actually see the person and I can use my gestures to, that it feels more like I'm actually with you in the room. We try to have a good internet connection that, well, at least we don't have these basic communication problems. And maybe have some other kind of help, like technological solutions that help you structuring your discussions more. There are some colleagues of mine in the US that, for example, for this kind of design process, they propose to have certain reminder cards. It's basically like a card game. So when you go through this process of designing, you just now and then pick one of these cards and it says, have you thought about your overall assumptions? Maybe go through these 3 points, think about it again. So kind of structured ways of supporting you so that you don't have the same technological issues that you usually have. The other thing is, of course, for companies that think about outsourcing or that are outsourcing, and that's difficult in the pandemic, is to consider, well, maybe if we have to solve problems, if we do tasks that require really creative work, lots of problem solving, we should try as much as possible to have them in a co-located setting, to actually get together, discuss it in the same room, because it's just always going to be more effective. And the issue with this overall, if you're not aware of this, and if you don't try to solve the technological issues, is of course, you will reach some conclusion. So in the software world, this means you will eventually build a system. There is a good chance that you will succeed. But if you consider that you have actually skipped a lot of the problem space up here, or you haven't thought about it enough, you might actually run into the issue that a lot of underlying problems are not discovered, a lot of assumptions might be wrong, and that of course might cause lots of problems later on, that you have a software system that doesn't work as intended, that is not suitable for the people that should use it, and that essentially leads to further challenges. So that's overall the takeaway challenge. And even though we haven't studied communication in general, there is a lot of existing work. So you can at least now have an idea of why remote calls with your mom or whoever feel so much less effective than when you are in the same room. You are essentially not going into the problems as much. You're just discussing the solutions or the outcomes. This was an extremely short presentation of quite a deep topic, so there's definitely more there. It was work that I did with a bunch of people, excellent people all over the world, talking about remote collaboration, so this is not me alone. And if you want the full story, there is a paper that you can read. I guess we'll publish the slides as well, so you can look into the entire paper if you're interested in. And I'm always happy to talk, so if you want to discuss this further, you can reach me through various channels or just drop by the university if this is possible again, so that we can actually solve the problems face to face. I believe that's it from me. Time is up, so I'll be looking forward to questions later on. Thank you.
Thank you very much, Grischa, for reminding us that if you're not part of the solution, you're part of the problem. But it was an excellent presentation, so let me clap on behalf of everyone. The third and last speaker of this Spreading the Computer Science Gospel event is Henning Úlfarsson, who's going to tell us about what mathematicians can learn from computer scientists. Henning, the floor is yours.
Thank you, Luca. I'm going to start by sharing my screen. Go through some math with you. So what can computers teach us about mathematics? Well, I'm part of a research group called the Bermuda Triangle, which you can find on Google if you ignore Google asking you whether you actually meant the Bermuda Triangle. This is a group of mathematicians who are trying to get away from doing their job by making computers do their job for them. And we are currently working in a subfield of mathematics called permutation patterns. This is a typical small subfield of mathematics. It has a yearly conference and approximately 100 active researchers spread all over the world. Historically, Iceland has actually been a big component of the research work in this field. Now, I'm going to give you some of the core definitions, but like the other speakers, we don't have much time. So I encourage you to ask me or ask the internet about this field if you find it interesting. So the core definitions here, for starters, a permutation is something that permutes. Not surprising, but what does that actually mean? Well, let's take the integers 1, 2, 3, 4, 5. Then we can move them around, permuting them in some way. You don't all have to move. We can move 4 just to its original spot. And you have a permutation of 1, 2, 3, 4, 5. Another way to think about this is that 1 is being mapped to 3, 2 is being mapped to 5, 3 is being mapped to 1, 4 to itself, and 5 to 2. And to describe the permutation, we're often just lazy and write just this bottom line here. And since we're permuting the integers 1 to 5, we would say this permutation has length 5. And of course, there are shorter permutations and longer permutations. I also mentioned patterns. So what is a pattern in a permutation? It's a smaller permutation inside the bigger one. So if you erase the 3 and the 4 from the big permutation, you're left with 1, 2, and 5, and you can track where they go. And if you're just moving around 3 numbers, it's enough to just work with 1, 2, 3 and permute them the same way as you did inside the larger permutation. And this gives you the small permutation 3, 1, 2, which you could say is a pattern in the larger permutation. So the large permutation contains the smaller one. If you cannot find the small one as a pattern in the big one, you would say the big one avoids the small one. Okay, if you like drawing things, you can view this graphically. Here's a graph of the large permutation, and I've placed black dots here for the large permutation. I've started with 3, height 3, because that was the first entry in the permutation. Then we have height 5, height 1, and so on and so forth. And if you focus on the same pieces of the big permutation like we did above, and you ignore the other dots, then you're left with something that looks like the permutation 3, 1, 2. So that's just a re-derivation of what we did above, but now with pictures if you prefer that. We can now state the central question of the field. For a fixed pattern, how many permutations avoid the pattern, meaning do not contain it? Now let's answer this question for some simple cases. If you're trying to avoid the pattern 1, that's actually pretty hard, because any point in a permutation can play the role of the pattern 1. So all permutations contain the pattern 1, unless the permutation is completely empty. So you write 1 here for the empty permutation that avoids the pattern. You cannot find any other longer permutations that avoid the pattern 1. In particular, here for length 5 permutations, there are no permutations that avoid 1. And I'm going to write some stuff here in this column later. If we move to slightly longer patterns, we have these 2 symmetric patterns, 2, 1 and 1, 2, which you can see will provide the same answer if we're counting the avoiding permutations. Let's think about the pattern 2, 1. I'm claiming there's a single permutation of length 5 that avoids this pattern, because that's going to be the permutation 1, 2, 3, 4, 5. that is the only permutation you can write down of length 5 that avoids having 2, 1. Because of time, I'm not going to explain that any further. Moving ahead, Knuth in 1968 considered the pattern 132 and found that the number of avoiding permutations behave like this. And these are the famous Catalan numbers, which you might have run across. And approximately they grow like 4 to the n, which means that if you're thinking about length 10 permutations, they are very roughly 4 to the power 10 many. More recently, people have been studying longer patterns and answering the central question for them until they got stuck on this problem, 1324. You can brute force the answer pretty far, but no one has been able to give a precise answer for how many these permutations are that avoid this 1324 pattern. In fact, one of the famous mathematicians in this field, Seilberger, has said not even God knows how to solve this. Of course, we're trying to answer this question. We haven't figured out the answer yet, but in this talk, I'm going to focus on this piece. As you can see, Bona answered this in 1997. And what he did was he built a very nice but complicated theory using bijections to something called beta trees to give the exact enumeration of the permutations avoiding this. And this problem is important enough that people have been trying to find alternative proofs ever since. For example, Bloom and Elizalde in 2013 gave a different solution using a different kind of theory for the same question of these 1, 3, 4, 2 avoiding permutations. Now, our approach to this, and actually the field in general, is to build powerful algorithms and software to search for simple solutions. There's a lot hidden in these words search and simple. And let me explain first what I mean by simple. A simple solution for us can be large, but each step in the solution should be simple. Again, I don't really have time to explain exactly what I mean, but here is an example of a simple step where you start with this, and for example, you pull out the single point and write this as a product. Mathematicians will know what I mean. And here on this page is actually the full solution to the problem originally solved by Bona, where each step is quite simple, no heavy theory necessary. So that's what I mean by simple. What do I mean by search? Well, we run our algorithm for a few hours on a machine with enough memory, which can sometimes actually go up to hundreds of gigabytes. We create a few million steps that could assist in finding the solution, and then we pull out a small set to build a solution like the one you see here. And in this particular case, this was actually discovered last week by our algorithms, that it is in fact possible to answer this case of 1342 with simple steps. And we're of course pushing forward, attempting to try to solve the almost impossible case of 1324 that people have been trying for at least 50 years. And one nice thing about our approach is that it is, in a sense, domain independent, but we've only implemented an interface to the subfield which we are most familiar with, the permutation patterns. Other areas await. Thank you for your time, and I believe now is time for questions.
Thank you very much, Henning. I'm waiting for the Quanta magazine article on your discovery. It will happen at some point soon, I'm pretty sure. As Henning already said, the floor is open for questions from the audience. I suggested you either raise your hands. I don't know whether you can unmute yourselves actually, but otherwise we get Grischa as a host or co-host to unmute people or whoever wants to do so. You can also post your questions on the chat, and we can repeat them. So while we wait for questions from the audience, I guess it's my role as session chair to sort of break the ice. So let me go in the order of presentation, and I start with a question to María. I'm not going to ask you sort of what people in different countries actually ate to gain those 100 grams or 200 grams, whatever it was. But do you have any data about Iceland from whiting?
No, unfortunately not. These are just numbers that V-Things published. I left the link on the slides if you want to take a look. But no, I don't think there are any numbers for Iceland. Iceland is often left out in these aggregated numbers because we are so few. Mm-hmm. For example, we were included in these Apple data, but Google published a similar data set where they showed these trends for people like going to work or going to different places, different types of places. And there Iceland was left out, and I think it's because we are just too few and there's a risk of being able to identify someone. So I know, unfortunately, V-Things did not publish this number for Iceland.
I also remember there was a study by a group at Berkeley, I think it was Xiang and his group, who studied the effect of the lockdown measures on the casualties mm-hmm. that could result from COVID. Yeah. What kind of data set did they use for that purpose? Is it similar data set that you were using, or was it different?
I'm not sure exactly, but I mean, there are researchers that are using more fine-grained data sets about the mobilities. I know there's a project at MIT Media Lab where they are using an app similar to Foursquare, where they have more detailed information about individuals' movements. But I don't know what it was in this particular case, unfortunately.
Thank you, Maria. So while we wait for further questions, I can move on to Grischa just to continue in the order of presentation. Grischa, very interesting presentation. I was wondering, you suggested that we could put more structure into our online problem-solving sessions so that we explore the problem space more thoroughly than we normally do. Have you conducted any experiment, or has anybody conducted any experiment on the effectiveness that structure actually has in the exploration of the problem space? For instance, this idea of reminder cards that you actually mentioned.
There are, I don't 100% recall whether they also did it in a distributed setting, but these reminder cards have been, they haven't only been proposed, they have been evaluated and found to be rather useful. I'm not sure in the area of software engineering whether there have been any studies on this. I'm pretty positive that in the communication area in general, which is of course highly interdisciplinary, there are studies. I don't know any concrete ones though, so we would have to look at that in more depth. I mean, but I think there is a lot of unsystematic evidence, a lot of experience that people have, that at least the basic structure can help them. I mean, a very good example is exactly what we do here, that you mute people and you have to raise your hand. That's already a way of structuring the overall process that has clear benefits, because you don't have these interruptions anymore. But going more really into the specific topic of whether you do more problem or solution space exploration, I'm not aware of anyway.
Thank you. And now I'll conclude my round so that I give people time to think with Henning. Henning, you showed us an example of a seminar result in your field that can now be shown algorithmically using simple steps by your algorithm. You also mentioned two human proofs that were given by Bona and by Elizalde and Bloom, or Bloom and Elizalde, just to say it in alphabetical order. Sort of, how does the proof that is generated by the algorithm compare with the two human proofs? Or in other words, is it more similar to the Bona proof or to the Bloom-Elizalde proof, or is it different?
It is completely different.
And now for something completely different.
Yes. So, as I said, it's only using simple steps, although it's very hard to find. That in itself is not surprising, because it's a hard problem and you should expect it to be hard to find a simple proof of a hard problem. Mm-hmm. But you can't really map it onto the theory in either of those proofs.
So that makes it even more interesting. Sort of simplicity is hard to find.
Yeah, and it was actually very surprising to us as well to be able to find this, because we've been looking for proof in this particular case for 7 years probably.
There is a question from María. María, do you want to ask it yourself? Since
Sure. I was just wondering, because you gave us, the idea at the end of the presentation that you could apply this in different areas as well. Do you have any suggestions for that?
So the main application areas currently would be other fields where you can easily get a hold of descriptions of problems that you can make the computer understand and manipulate. Mm-hmm. The algorithm is basically splitting a problem into subcases, finding equivalent descriptions of subcases in a different format, building other subcases of those subcases, and so on and so forth, building this universe kind of a logical steps, and then searches for a solution inside that universe. So whatever you can implement, really, you can apply this to.
I would have a question as well, talking about other application areas, since in my area in software engineering, there's this growing community of what is called search-based software engineering. So they basically try to find solutions to, for example, how do you do testing by searching. So I was actually wondering, what kind of techniques do you do on the search side? What are sort of your search strategies? How you go through this space and try to explore it?
Yeah, so the kind of heavy part of running the algorithm currently is building a universe of these logical connections. And we fine-tune how that universe is built by loading in different strategies. This heavily affects the size of the space, the breadth of it, the depth, and how long it takes to compute. When you actually have a hold of this space, what we do is we prune away all the objects that you cannot understand. And you do this very often throughout building up the universe. And if you suddenly reach a stage where the original problem is one of the explainable objects, that's when you output an explanation. So we're not actually using any fancy search techniques at the moment, but that's a future area of research where we are a bit smarter in the search, using some kind of techniques from AI, for example.
All right, thanks.
Okay, so if there are no further questions from the audience, let me thank the speakers for their excellent contributions to the third Spreading the Gospel event, the participants for showing up in good numbers. If you enjoyed this event, spread the word. There will be a similar one towards the end of our semester, probably in November. We haven't planned anything yet, but either in November or December, we'll have the fourth edition of the Spreading the Computer Science Gospel event with excellent speakers and interesting topics. So thank you very much to everyone, and enjoy the rest of your afternoon.